So in this section, this is still section 3.4, but now we're going to focus on solving logarithmic equations. So before, when we solved exponential, we used logs. Now when solving logs, we're going to use exponential equations. To do this, we need to do something called exponentiation, which is writing a log in exponential form in order to solve it. So it's like we're rewriting the log as an exponent in order to solve the equation. It's applied after the logarithmic expression has been isolated. So just like with exponential equations, when we wanted to get the base and exponent alone, we want this log to be completely alone. And then once again, we're going to review the log properties. You don't have to write these down. They should already be in your notes. But the two we're going to use are the one-to-one and the inverse property. So for the one-to-one, if you have a log with the same base, so log base a of x equals log base a of y, then that means that x must equal y. So anytime you have log base something equals log base something, you can set those values equal to each other. And same thing goes for ln. The inverse property is what we use to cancel out when we have a log base, whatever. And how we do that is by making the log an exponent. So a base of a log base a of x would just cancel out to equal this x value, which is what we're solving for. So anytime we're solving an equation, we're solving for x. So we need to use a base of a with a log base a to cancel out to equal x. So now we're going to do some equations, help get ourselves used to this. So the first one we have is the ln of x minus the ln of 3 equals 0. So what we are going to do is, to make our lives easier, why don't we add the ln of 3 to the other side? So we're going to add the ln of 3 to both sides. On this side, it cancels. And on the right side, we get the ln of 3. So what we're going to do now, because we have ln and ln, which has a base of e, matching bases, we can set x equal to 3 as our final answer. And we're done. Here we have the ln of x equals -3. So in this case, our log is completely alone. We can't use this because we don't have an ln on the other side to match. So we need to use a base of e to cancel out this ln. So e, and we're going to raise it to the ln of x. And we have to do the same thing on the other side to keep things equal. So e -3. So whenever you're solving for logs, this whole part of the equation becomes the exponent with whatever base cancels this log. So those cancel out. We're left with x equals e to the -3, and that you can do in your calculator. When you plug that in, you should get 0.050 about. Same thing over here. So log base 10 of x equals -1. So what is going to cancel out a log base 10 here? It would be a base of 10. So we take 10. This whole thing becomes an exponent. And same thing to the other side. 10, that whole part becomes an exponent. Cancels. We're left with x equals 10 to the -1. You can either plug that into your calculator or you can do it in your head and say, oh, that means that it is 1 over 10. Or you did on the calculator, 0.1. All right, so here, more logarithmic equations. We have the ln of x equals 2. So we have our log and x alone. What cancels out an ln? It is a base of e. So we have e as our base. This whole thing becomes the exponent. Same thing on the other side. E as our base. That whole piece becomes the exponent. So keep in mind, this whole thing should always be up in the exponent now with whatever base cancels this out. Cancels, we get x equals e squared. We can plug that into the calculator and we get 7.389. So I'm also rounding to 3 decimal places here to keep it consistent. For e, we have the log base 3. 5x minus 1 equals the log base 3 of x plus 7. So you can do this one of two ways. You can either raise both up as exponents with a base of 3. So like this. I'm just going to write this as if these are now exponents. You see that these both cancel. Or if you know the exponential identity, you know that if the log on both sides of the equal sign has the same base, these parts are automatically equal. So 5x minus 1 equals x plus 7. So this actually proves why this whole thing works, why this must equal this if the bases are the same. Because if you raise both, exponentiate both, with that base, it's going to cancel out both of them. And now you solve this like a regular equation. So subtract x from both sides. We get 4x minus 1 equals 7. We're going to add 1 to both sides. 4x equals 8. And look at that, a nice whole number. We get x equals 8 over 4, which is 2. All right, so we have 5 plus 2 ln x equals 4. So in this case, my ln x is not alone. So what we need to do first is get rid of this stuff. So first, I'm not going to add the 5 plus 2. You do not want to mess with that. You want to just start bringing stuff over to the other side. So I'm going to subtract 5 from both sides. We get 2 ln of x equals -1, and then divide by 2. So I get the ln of x equals -1/2. So ln of x is now isolated. The base that cancels out in ln is e. So e to the ln of x equals e to the -1/2. Notice this entire thing becomes an exponent with a base of e. Cancels. We get e equals -1/2. Or x equals e to the -1/2. If we plug that into the calculator, we get 0.607. All right, moving on. So 2 log base 5 of 3x equals 4. So this 3x is all part of the log. So the only thing we need to get rid of is this 2. So we're going to divide by 2 because you need to isolate the log before you exponentiate or before you raise everything up. All right. So now we have the log alone. So we're going to take 5 as our base and we're raising everything up. All right. Cancels out. We get 3x equals 25 because that's 5 squared. So now we're going to divide by 3. Divide by 3. So x equals 25 divided by 3, and you can actually just leave it as a fraction, or if you really wanted to, you could also get it as a decimal. But this is a fully simplified answer. So now, checking for extraneous solutions. So since logs have a restricted domain, we need all values to be, if we're taking the log of something, it has to be positive values. We have to check for extraneous solutions to make sure the solutions we get aren't going to make our log negative. So here the domain is generally does not include all real numbers because it doesn't include negatives. So we must check to see if when we plug in our answer, if we get a negative log. So here's an example of that. Now this is a little bit of an intricate example. We actually first have to start by condensing this into one log. So if you remember, when we are adding logs, we can condense them using multiplication. So I'm going to write this as 1 log. So I get this. The ln of x minus 2 times 2x minus 3 equals 2. ln x. So now what I'm going to do is I want to take this 2 that's in front of this ln and I want to make that an exponent. Because in order for us to combine both sides, um, I want to have the same ln and ln on both sides, so that we could set this equal to whatever this is. So now what I'm going to do on this side is I'm actually going to FOIL out. So I get 2x squared minus 3x minus 4x plus 6 equals the ln of x squared. And here we can combine like terms, so we get the ln of 2x squared minus 7x plus 6 equals the ln of x squared. So what we end up with is, since we have ln and ln on both sides, we can set this equal to this. So I'm going to do that right down here. 2x squared minus 7x plus 6 equals x squared. And now we're going to start to solve this like a regular quadratic. Subtract x squared from both sides. So this leaves us with x squared minus 7x plus 6 equals 0. So this is not our final answer because we want to solve for x, but here we can now factor. So in order to factor this, put it right over here. We have x and x, what adds to 6 and or multiplies to 6 and adds to -7, it would be minus 6 minus 1. So we get x minus 6 equals 0, x minus 1 equals 0, which means x equals 6 and x equals 1. So what we're going to do now is we're going to check to make sure that this works in our equation. So let's start with x equals 6. If I plug in a 6 here, a 6 here, and a 6 here, let's think about this. So here, this is going to be positive. 6 is a positive number. Here, I get 2 times 6 is 12, minus 3 gives me 9, positive number. 6 minus 2 is 4, positive number. All right, 6 checks out. Let's try 1. So 1, 1, 1. 1 here, positive number. So that checks out here. 2 times 1 is 2, minus 3 is -1. So here we have the ln of -1, and here we have the ln of -1, which does not work. So that would mean x minus 1 is an extraneous solution, and our only answer is x equals 6.